afternoon, everyone. Thanks for attending our seminar. We are very happy today to have Dr. Neil Chada from the King Abdullah University of Science and Technology. He's going to give us a talk on unbiased inference for HMM diffusions. And before Neil starts, I will give a brief introduction of Neil. And I believe Neil got his PhD from University of Warwick. And then he worked as a postdoc fellow at the National University of Singapore. And after that, he moved to the King Abdullah University of Science and Technology. And yeah, all yours.
Thanks, Jinglai. So hello, everyone. Thanks again to Jinglai for the introduction and the invitation to speak here today. So just 1 minute. Yep. So it was a coincidence when I got this invitation because I was actually watching some of the talks from the seminar series. And I must say that from the discussions, presentations, and the speakers who came to present, I found it all very interesting. So it's very nice to be presenting here. And thanks again for the invitation. So the theme of the presentation that I'm going to show you today is more so on the computational statistics side. And the reason for this is because from the talks that I've seen in this seminar series, most of them have been on the application of mathematics to data science and machine learning problems. So therefore, I felt it was nice just to go to the other research theme, which is computational statistics. And I think the topic that I've chosen for this presentation really matches that. And for this presentation, what this talk is going to be interested in is a class of models, which many of you I'm sure are familiar with, which are diffusion processes. And diffusion processes are very interesting because they have a high level of applicability in a wide range of applications. Most notably, that being mathematical finance and also applications to illogical and biological processes as well. And in particular, for this presentation, I'm going to consider the unbiased inference of diffusion models, in particular, partially observed diffusion processes. So the field of unbiased inference for Monte Carlo methods has seen a lot of attention in the last 10 to 15 years or so, notably because of how challenging it is, but as well as this because how useful it is if you want to discretize particular methods, Monte Carlo methods for numerical investigations. And what I hope to show you from this presentation is that me and my co-authors are able to do unbiased inference for partially observed diffusions, where we actually take motivation from techniques from uncertainty quantification and operations research, and we are able to extend some of the current ideas which they have in the current literature for unbiased inference for stochastic differential equations. So this leads to the title of today's discussion, which is Unbiased Inference for Hidden Markov Nodal Diffusions. And I should say that this is joint work with a number of individuals, Jordan Franks, who I believe is still based at the University of Newcastle, Ajay Jasra, who is based at also the King Abdullah University of Science and Technology, Cody Law at the University of Manchester, and Matti Viola, who is based at the University of Jyväskylä. Oh, sorry. So the bulk of this presentation can be found in this recently accepted preprint, which has been accepted into SIAM ASA Journal on Uncertainty Quantification. And really, this paper covers everything that I'm going to discuss in the presentation today in a very brief sense. I would recommend anyone this paper if they're interested in finding out more information, especially on the methodological and also the computational aspects of the paper as well. But aside from this paper that I'm going to present, I want to emphasize that two key papers in our understanding for developing this paper and the ideas in the paper really come from these two pieces of work. The first is based on the co-author of Matti, where he shows a connection between multi-level Monte Carlo and unbiased estimation, which was published in Work of Operations Research. And as well as this, the work of Rhee and Glynn, which has really revolutionized the way that one can think of unbiased estimation for stochastic differential equation models. And just to give you a little bit of a brief outline of what the talk is going to consist of, I'm going to begin with a review of hidden Markov model diffusions with some motivation of why one would be interested in this. I will then discuss the challenges which can arise from this when trying to do inference or in general unbiased inference for these processes, and then discuss the actual steps that me and my co-authors will take in order to overcome these issues, where we present some theory to indicate that what we're actually doing is what we want, and as well as there's some numerical verification which showcases what we're doing, well, the theory actually works in practice as well. So as I mentioned, the class of models that I'm interested in are partially observed diffusion processes. And this is a class of a diffusion process where diffusion processes generally take the form of the very first equation, which is a stochastic differential equation. So the process of interest that we have here is x dash of t, where x is a diffusion process, and a dash of t is essentially known as the drift term, and b dash t is known as the diffusion coefficient, and wt can be some cylindrical Brownian motion. And these models, as I mentioned, are very applicable. But with partially observed diffusions, and related to this talk, what we're actually interested in is filtering and the use of stochastic differential equations, or the continuous time segment filtering. And so what filtering is concerned with is essentially either state estimation or parameter estimation of a dynamical system. And usually in the context of these Monte Carlo schemes, what you're trying to do is trying to combine two different processes for better joint inference. And these two processes usually take the form of a signal process, which I denote as x or x dash of t on this slide, and an observational process, y of t. So the idea is that we have some information about x of t, which is in the form of y of t, which you can see right here. And then using that information of y of t, we actually improve the inference of x of t. And in a Monte Carlo setting, this actual inference over these equations that you see, or these processes, is in the form of a probabilistic distribution of x of t given y of t. And specifically for partially observed diffusion processes, what we have is that the signal process here is given as a continuous time process or a stochastic differential equation. And the observational process here is given through partial discrete time observations. And this is using the information of the signal. So the key point that I want to emphasize with this slide is that if we're considering partially observed diffusion processes, we have the signal process, which is a continuous time process, and y of t, which is a discrete time process. And as shown at the very bottom, this picture that you see right here is a general picture that you can think of for a hidden Markov model framework, where we don't have direct access to X, but what we do have access to are partial observations based on these signals, which I denote by Y. Okay, so we're interested in essentially inference over the process of X of t, which is actually gaining information from the observations Y. So we're interested here in the filter and distribution, which I'll get onto in a minute. So like I said, there's a huge range of applications for diffusion processes. Many of you would know these processes given your background in both computational statistics and applied mathematics. But just to say that the initial role of filtering and hidden Markov model diffusion processes really came about in the field of numerical Weber prediction, NWP, and geophysical sciences. So a lot of, let's say, climatology offices that you would get, such as the Met Office in the UK and other offices worldwide, would generally use these climate models, and they would be interested in actually simultaneously trying to gain inference on the overall unknown by incorporating information from the observations. And essentially this is known as filtering or data assimilation as well. And this idea and notion of filtering has been very popular in numerical Weber prediction, where common models which are generally used include the Navier-Stokes equation, different Lorentz models as well. Other applications that I mentioned include mathematical finance, where one is interested in option pricing or even interest rate models. And generally what is done is trying to gain some information or idea about correlations in mathematical finance. So what I've actually provided in this bottom picture is essentially the relationship between the FTSE 100 and the actual currency exchange between the Great British Pound and other currencies as well. And as you can see from this picture, that they're actually inversely correlated. So in other words, if the FTSE 100 tends to decrease, then we start to see an increase with the exchange rate of this blue curve. And the opposite, of course, also happens in the opposite effect. In other words, once this decreases, this starts to increase as well. And this relationship or correlation that you have between these two curves, which is the red and the blue one, can actually be modeled quite well using hidden Markov models. And more recently, a very interesting application to many people in this field would be machine learning and data science, such as natural language processing. So natural language processing is the science of robots trying to communicate with humans. So for example, if you take Siri on your Apple phone, or if you take Amazon Echo and you're interested in giving it a command such as what is the weather today, or can you tell me when is the next cinema time for this film, it will try and process the information that you've given and try and come up with a response. And this communication is known as natural language processing, which actually uses the framework of hidden Markov models. So there's a huge array of applications, which is the purpose of this slide that I've given. And I'm sure there's a lot more applications as well, which I'm not familiar with or I'm not known, but definitely use the ideas of hidden Markov models and also filtering as well. So I've given you the model class that I'm interested in, which is partially observed diffusion processes. And of course, the obvious question is what we're interested from this. Well, as we're interested in Monte Carlo methods, numerical Monte Carlo methods, a very common goal, or the common main goal.
Sorry, Neil, can I ask a question here?
Yeah, of course.
Yeah, can you go back to the previous page? I'm just curious, in the example you are given here, which one is the hidden process and which one is the observed ones? Because it looks like you can observe both, right?
You can observe both. I'm not so familiar which is the observed and unobserved process, but from my knowledge anyway, and from what people have told me, is that you can actually use the exchange rates in a hidden Markov model framework. So I'm not an expert in this, and I couldn't tell you exactly what is the unobserved or the observed, but there's many papers which use this framework in both interest rate models and also currency exchange as well.
Yeah. Yeah. So the observed one should be kind of conditionally independent from the kind of a previous state, right? I mean.
Yes, it should be.
So basically, y is conditional on x, which is independent. Y t plus 1 is independent of y t, conditional on the variability of xt or xt plus 1 with it. Yeah. So which yeah. So
you're right in what you say. The actual image that I gave is not to indicate that one is an observed or one is an unobserved process. It was just a cartoon to demonstrate that there are applications in mathematical finance. The exact applications and the exact theory which is used to describe either the observed or unobserved, I don't know myself. I haven't any previous experience with, but yes, you're right. It should be conditionally independent.
Yeah, thank you. Yeah.
So yes, as I was saying, the model class that we're interested in are partially observed diffusion processes. And the main goal that we're interested in, likewise with many numerical Monte Carlo methods interested in sampling, is the goal of Bayesian inference, where we're interested in actually representing our unknown, or we want to do our inference, where we take into consideration both the signal process and the observational process. And this is known as the posterior distribution. And then through an application of Bayes formula or Bayes rule, we can express this posterior distribution up to some level of proportionality, which includes a prior distribution, which is just a distribution which says some initial belief we may have about the underlying distribution and the likelihood, in other words, where the actual data comes in as well. So this is just a few basic equations trying to indicate what the posterior distribution is. And because we're going to be dealing with particle filters and sequential Monte Carlo methods, which I'll explain in a few slides on, a very common way to express sequential Monte Carlo methods or particle filters is through this Feynman-Kac formulation. And this Feynman-Kac formulation is used by many people, both practitioners and theorists, where they use this specific notation. So as you can see right here, G represents the likelihood that we have, which is, of course, the data conditioned on X at the discrete observations. Eta theta 0 is essentially the initial distribution that we have. And this is the Markov kernel, which goes between essentially one state x of p, or one state x of p minus 1 to the next state x of p. So this is the general form that we're going to take for the actual inference that we're going to do in the next few slides. And I can always refer back to this slide if anyone is confused. The notation used for this actual, in practice for particle filters can be confusing, but to ease things for the audience members, I'm only really going to use M and G here, where G is for the likelihood and M is just for the Markov transition kernel on the state space capital or bold X. So that's the notation that we're going to consider for this. But of course, what we're really interested from this talk is unbiased inference. And of course, why unbiased inference is very important is because when you try to discretize some model, whether it's a stochastic differential equation or another model such as a PDE, there is a discretization bias that you use based on that discretization scheme. So for finite element and finite volume methods, of course, this will depend on the specific method. And for the class of stochastic differential equations, this will, of course, be the Milstein scheme, the Euler scheme, or whatever scheme that you've used to discretize the SDE. And of course, it's very important to try and remove this as best as you can to get a more accurate estimation of what you want. And so the ideas of unbiased estimation in Monte Carlo methods really go back to the ideas of Gareth Roberts in 05 and 06, where himself and his authors, both at the University of Lancaster and the University of Warwick, tried to perform exact simulation from a stochastic differential equation. Now, of course, if one is interested in exact simulation, you want to remove any notion of discretization bias that you may have dependent on the actual methodology that you use. And what he proposed with co-authors in 05 and 06 was to actually come up with a way to do exact simulation for very simplistic stochastic differential equations. And indeed, him and his co-authors were successful, and they labeled this method as the exact method. And what the exact method does essentially is that it uses ideas from, it essentially uses a transformation of the stochastic differential equation, where you apply a Lamperti transformation onto your stochastic differential equation, and then you do some accept-reject schemes, such as rejection sampling, to see if you actually take samples from this transform scheme. And then what you do afterwards is that you take the inverse Lamperti transformation from this, and then from that, this three-step process, you actually get exact simulation from your stochastic differential equation. So it's very nice that this methodology actually works, but like I said, it works primarily for simplistic stochastic differential equations. So what do we know about this technique more generally? Well, the first important thing is that it will work, generally speaking, for one-dimensional stochastic differential equations, and it will work for Gaussian dynamics and also sometimes non-Gaussian and non-linear dynamics. But the main crucial aspect and where it doesn't work is actually in multidimensional stochastic differential equations. And the reason why it doesn't work for multidimensional stochastic differential equations is because once you actually take this transformation to get the exact samples, which is the Lamperti transformation, it actually, once you do this transformation, it actually turns the diffusion coefficient to a constant diffusion coefficient. And as well as this, it actually transforms the drift term into some gradient of the potential function. So once you have this transformation, the drift turns to a gradient of a potential function, and the diffusion coefficient turns to a constant diffusion coefficient. Now, this is very good if you have stochastic differential equations of this form, but in the cases where you don't, which is not the case for many multidimensional stochastic differential equations, this can be a problem. So given the difficulties which have arisen from this exact methodology, what we are trying to do and really propose from this work is try to move away from this, where we can do unbiased inference, or in some naive way, exact simulation of d-dimensional stochastic differential equations where d is greater than 1. And of course, the question from this is, how do we actually do this in our work? Well, we can do it with our work, and the approach that we consider really takes, as I mentioned at the beginning, motivation from different areas of mathematics, both for uncertainty quantification and operations research. So the three ideas that we use essentially for this is that we base this on Euler approximations of stochastic differential equations, which is the first bit. And then once we discretize these SDEs, which I'll explain later on, we actually use a de-biased multi-level Monte Carlo scheme, which is really combining the ideas of multi-level Monte Carlo and de-biased Monte Carlo for stochastic differential equations. And then at the very end, we use some recent work which has been developed in the computational statistics community, which is an important sampling type correction, which will make sense later on as I describe it. So even though these are the three techniques to our approach that I've showed you, the three real approaches that I'm going to use is a de-biased scheme, a multi-level Monte Carlo implementation where we combine these two, and then finally an important sampling type correction as well. So this is the main crux of what the approach is going to consider in order for us to get unbiased inference for partially observed diffusion processes. And essentially this slide just verifies what I've just essentially said. So what we're going to consider at least is two phases. We're going to split up these three ideas in our approach to two phases to simplify things. The first thing that we're going to do is actually we're going to run a particle marginal Metropolis-Hastings method. So this is a particle Markov chain Monte Carlo method, which actually the idea behind it is to use SMC as a proposal distribution within your Markov chain Monte Carlo method. And this can actually improve the performance of your Markov chain Monte Carlo scheme. And as well as this, these particle MCMC methods have shown to work very effectively when you're trying to do joint inference, depending on what your signal and observational process is. So if you recall, right here, from the joint inference that we're interested in, it's regarding both theta, which are parameters of the diffusion process, and x, which is just given by this right here. So we're interested in joint inference, and it makes even more sense to consider particle MCMC because it has been shown to be very effective for joint inference as well. And from this, we consider a coarse level Euler discretization scheme, which is just using the Euler-Maruyama scheme for stochastic differential equations. And then again, from this, we use the three techniques that I've mentioned, which is the IS-step correction scheme, a debiased scheme, a multi-level Monte Carlo scheme, where we implement these ideas together. And then hopefully by using these techniques, initially, we wanted to know if they were parallelizable and also scalable. And as I'm going to show you later on, it is the case that we actually can gain these two things through this unbiased scheme of PO, partially observed diffusion processes. So let's go over the first bit of the approach that I mentioned, which is simply an Euler-Maruyama approximation or scheme to the stochastic differential equation. And this is very simplistic. With what we have, essentially, we're just discretizing this scheme. And for anyone familiar with the Euler scheme, essentially, this is the form that it takes, where you discretize in time, where t denotes the discretized time step that you have. And of course, once you discretize this STU, you usually take the differences of the Brownian motion increments. And as we know from the definition of Brownian motion, that if we consider the variance or the difference in these schemes, then what we actually get is that it is normally distributed with mean zero and the variance h of L, where h is the discretization level that we have. And h of L also comes in the drift term, which we have right here. So just to mention again from this slide, M is going to denote the Markov transition between these two states, x of p minus 1 and x of p. We also have a latent probability. And what we're trying to do is an approximate joint inference over the posterior pi of L using particle Markov chain Monte Carlo methods. So now let's get into the main bits of what's actually required in us for us to do this unbiased inference. So the first thing that we need is multi-level Monte Carlo. And multi-level Monte Carlo has been a very popular and very powerful applied mathematical methodology, which was first proposed by Hendrik and Giles in the early mid-O's. And I won't go over the full details of what multi-level Monte Carlo is concerned with, but just to give you a one-slide introduction, as I've put on the slide, the central idea behind it is to reduce the cost associated with a Monte Carlo method while maintaining a certain order of a mean square error. So if you want a particular order of an MSE from your Monte Carlo method, but it's quite costly to attain this MSE, instead what you can do is apply multi-level techniques to the Monte Carlo method, which will result in an MLMC scheme. And then using that multi-level Monte Carlo scheme, what you can do is actually reduce the cost specifically for attaining a specific order of the MSE, where the order is of order epsilon squared for epsilon greater than 0. And so just to motivate how we could actually do this, let's say we're interested in approximating this expectation for this quantity of interest, which we denote by P of phi. Now, of course, to actually compute this expectation can be quite difficult, especially if what you're interested in can be quite intractable. So what is commonly done with Monte Carlo methods to approximate this is to take a series of approximations where L essentially denotes the discretization level that you have. So of course, if you increase the discretization level, even though it's more costly, you get an improved performance, generally speaking. And if you are interested in this approximation P of L, where L is the discretization level, then what you can do is actually express this summation for the approximation, where L is the finest discretization level that you use, and L equals 1 is the coarsest level. So this essentially is a telescope in sum. And this telescope in sum is a way to actually frame the approximations to a Monte Carlo scheme. And as I'm just going to state after this, this telescope in sum series is essential in order for the multi-level Monte Carlo scheme to work, in order to reduce the computational complexity to attain an MSE of order epsilon squared. So once you do this, if you use this telescope in sum, then what we're essentially going to say is that, okay, let's apply these multi-level techniques to essentially this approximation. And if we do this, then we have essentially the initial level which we have, which we're going to say is level L equals 0. And then for the levels L equals 1 to small m, we can use this telescope in sum idea, which we have right here, to actually represent the multi-level Monte Carlo estimator. And then through this, once you have the multi-level Monte Carlo estimator, of course, we're interested in the MSE. So we can express the MSE as this quantity right here at the very bottom. And as many of you would know, the MSE can be decomposed into two quantities. The first, which is the variance, and the second is the bias. And in the case that we have, this corresponds to the discretization bias of the stochastic differential equation. And so multi-level Monte Carlo is essentially a way of reducing the variance associated with Monte Carlo. And the way that it actually reduces the variance is by computing the variance of this particular estimator that we have right here. So instead of using the Monte Carlo estimator and computing its variance, instead we're going to use an alternative estimator in the variance, which will reduce the variance, and therefore with this telescope and sum idea, we can reduce the cost associated with for attaining a particular MSE of order epsilon squared. So this idea of reducing the MSE is quite crucial to this talk, because the other idea which I'm going to discuss about unbiased estimation is also very important. The MSE is a very important quantity for Monte Carlo methods, and one is always interested in reducing this quantity. With multi-level Monte Carlo, this reduces the variance, which therefore reduces the MSE. And therefore, as I'm going to show you later on, if we consider unbiased inference or de-bias schemes, this actually reduces the bias that you have from your discretization bias, and therefore it reduces the MSE even further. So in a mathematical or in a mathematical nutshell, one can say that the actual objective is really to reduce the MSE from this, but we're also performing unbiased inference over the posterior distribution of these partially observed diffusion processes. So this is multi-level Monte Carlo in a nutshell, where you're applying some telescope and sum, where you actually look at these couplings between these different levels. So this is at level L, this is at level L-1. And so this coupling, which is used in the actual multi-level Monte Carlo scheme through mesh refinement, is crucial for it to work. And so in order for us to apply this to the actual methodology that we're interested in, of course, we're interested to see how we can actually apply these couplings in the actual particle filtering scheme within the particle Markov chain Monte Carlo method. So if you remember before, M is the notation that we've actually denoted for the transition Markov kernel between X at state P-1 and X of P. So now what we're essentially introducing is this X cross, where X cross essentially corresponds to the difference between MP theta L-1 and MP theta L. So the cross just indicates the coupling difference between these transition kernels, and these definitions are just given right here, where this is MP theta L, this is MP theta L-1, so this is just essentially the difference between these two quantities right here. And this is how we actually incorporate the multi-level Monte Carlo ideas into the actual particle Markov chain Monte Carlo method. So this really covers the idea of the first bit, which is really required, which is multi-level Monte Carlo. The second bit, well, actually, before I get to the second bit, let me just briefly review the idea of particle filters and the method that we're going to use. So like I said, we are interested in particle Markov chain Monte Carlo method, which you can think of in a very naive way as incorporating SMC methods into Markov chain Monte Carlo methods. And the most famous SMC method is the bootstrap particle filter, where for anyone who is not familiar with the bootstrap particle filter, it is a methodology aimed at computing the filtering distribution, and how it does this is that it updates a set of particles and their associated weights based on importance sampling and resampling. Okay, so if anyone is familiar with Kalman filtering or ensemble Kalman filter, you can think of the ensemble Kalman filter as an equally weighted particle filter. So there's a lot of connections and relationships between filtering schemes, but the idea behind the particle filter is you update a set of particles as well as its corresponding weights based on two procedures, which is importance sampling and also sequential resampling as well. And so this is just a very generic algorithm for the bootstrap particle filter and how it's written. So let's say if we consider P equals 0, what we're interested in is drawing an initial distribution for an initial set of particles xi of 0. And of course, from this, what we're interested in doing is defining a set of weights from these initial set of particles. And then using this importance sampling type distribution scheme, then what we actually do is normalize these weights, and we update these weights based on the updating of the actual particles as well. So these updated particles can really be done through the resampling scheme, where if you have a lot of particles which don't have a lot of weights or nuisance weights, then what you can usually do in particle filtering is dispose of them, and you keep the weights with more weights or better weights, where there's a bigger emphasis of the distribution. And then through this resampling scheme, which you do for the weights, you compute through the particles, you compute the weights associated with these particles, and then your output essentially is just given by the updated set of particles and the corresponding weights as well. And so with this output, it actually satisfies for some particular function phi, where the expectation of this quantity right here, as at the bottom, which is the summation of these widths, as well as these particles, this expectation is actually just given as this posterior distribution, which you can see right here. So this is just to indicate that once you have the actual output, this is consistent with the filtering distribution that you're interested in, or the posterior distribution. And this is the bootstrap particle filter, but there's many more advanced particle filtering schemes that one can use depending on the applications, such as more advanced resampling schemes and particular applications as well. But the bootstrap particle filter is the particle filter that we're going to base our filtering methodology on in order to incorporate the unbiased and multi-level techniques. So what we're going to consider is essentially the particle filtering scheme for our coupling, which I've described here through the Markov transition kernels. And so what we're going to label this particle filter, it's known as the delta particle filter. And essentially the delta particle filter follows exactly the same procedure pretty much as the previous method, the particle filter. So as you can see, where we have an output of these set of particles and we have an output of these set of widths. But as you can see here, what we have, which is different, is instead of running the particle filter for M of P and G of P, as I've mentioned right here, instead we actually run this delta particle filter. Well, we run this particle filter, calling it the delta particle filter for M cross of P and G cross of P, where these are just defined previously over here. And then from this, what we have eventually at the very end is this output, which is the expectation of this delta particle filter, which is essentially, I don't think you can see it, but it's P of theta u. But now we have a coupling between the P of u theta between levels L and levels L minus 1. So the delta particle filter is exactly the same as the particle filter, except we introduce this coupling notion between the transition kernels and also the likelihood as well, which is given through M cross of P and G cross of P. Okay, and this idea of this delta particle filter has already been well studied in a number of works by A.J. Jasser and Cody Law, and they've shown that yes, it is still consistent with the filtering distribution and usual theorems that one would acquire with the particle filter. So it's not just that this method works in practice, theoretically, it has been numerically verified as well. So a lot of the theory is quite similar to the usual particle filter as well. And this is the particle filter that we're going to use, or the SMC method that we're going to use in our MCMC method. So that's the first bit, and also its inclusion in the methodology that we're going to use. The next bit, which is also very important and really goes to the heart of this presentation, is concerned with de-biased Monte Carlo. And de-biased Monte Carlo, as I've mentioned, goes back to exact methodologies proposed by Gareth Roberts, Fernhead, Papaspiliopoulos, Peskos, and other co-authors. But the work that we're going to consider based on the unbiased inference is actually work from Ryan, Glynn, and McLeish, where they consider de-biasing or unbiased inference for stochastic differential equations, which actually attain the usual square root Monte Carlo rate of convergence. And I would recommend anyone to read these papers because it's a very novel and neat idea what they do. It's a very powerful idea as well, and really extends the ideas of Roberts and co-authors like I've mentioned. And the central idea behind this de-biased Monte Carlo scheme is to produce unbiased estimators by introducing the notion of randomization. And I'm going to give you a very simple demonstration of how they actually do this through this paper, in their original work of Ryan and Glynn, which is demonstrated on this slide and the next slide as well. So let's say that we're interested in this expectation, which I've shown throughout the presentation at level L. And if you consider this expectation, then of course, let's say suppose that this expectation will eventually tend to this quantity of interest where there is no discretization level whatsoever. So let's assume this very simple quantity right here. And if we assume this simple quantity, then what we can also assume is that this expectation of delta L, where essentially delta L is just the difference or the coupling between these different levels. So if we assume this, and we also take this notation that we have right here, that's the first thing we do. The second thing that we do is that we're going to suppose that L is actually distributed according to some probability mass function, which we're going to denote by P of L. So this is where the randomization comes in. We're going to denote this as P of L, some probability mass function, which is independent of delta L. Now let's suppose that we define Z of 1 phi. The 1 here is not so essential. I've just labeled it as 1, but Yeah, let's just assume that it's z of 1 where it doesn't really have any significant meaning. And let's say it's given by the fraction of this essential quantity right here, which is a difference at the finest mesh refinement, and p of L. And so once you actually define this quantity.
Just want to clarify here. Sorry to interrupt. So the capital L is the total number of levels, right? Oh,
correct. Yes.
And so in that case, so in the first, not the first line, but so in the convergence, so the convergence is with respect to L or.
So this convergence can be small L or even capital L. It works both ways. It works
for. Curious, like if in terms of small L, this means like a capital L goes to infinity as well, right? Oh, that's.
For small L.
I just want to kind of understand the notation here, because you are talking about small L, then, yeah. What about the capital L?
So it should still hold for capital L. L is just some arbitrary level that I'm defining, and this is the highest level that I'm denoted by big L. So L is always bounded between 1 and big L. That's the notation.
Yeah, and then you assume that the big L is actually follows some given distribution.
That's correct. Yeah.
Okay, but in this case, it has to be the big L, right? Not the small L, right?
Yeah. Yes. Sorry, it has to be the big L. Yes.
Thank you.
Yeah. Thank you. Thank you for that. So it has to be the big L.
Maybe then I continue just to clarify again in the first line with the formulas, the P subscript U. What kind of thing is this? Is it an operator?
So this P of U essentially is, let's say, some probability distribution that we're interested in doing inference of.
Okay.
So in a Bayesian context, like a posterior distribution, you can think of.
And you evaluate phi with this distribution.
That's correct.
Yeah. Okay. Well, let's see. Okay, continue.
Okay, thank you. Okay, so if you define z of 1 to be this quantity on the right-hand side, then if we're interested in the expectation of this quantity, we can express it as this form, where in the numerator, this is essentially just an indicator function of big L being little l. And through this, we know that the expectation of this is just going to be the quantity inside we have. And then we know that this small p of L will cancel with this numerator. And then what we get at the very end is essentially a summation of the expectation of delta L. And as I've shown you right here, delta L is just given through this quantity right here, which of course will eventually converge towards this through this formula. And so what we have right here in a way is an unbiased estimation that we have using this particular formulation that we have right here. So it's very interesting that just through this simple idea of introducing randomization and labeling this as a new estimator, that by taking the expectation of this estimator, this actually gets the expectation of the original quantity that we're interested in, which is, let's say, some posterior distribution. And what that paper actually discusses by Rhee and Glynn is actually a theorem governing this idea behind de-biased Monte Carlo. So suppose that they assume that V is essentially the same quantity, except you take delta squared L instead, which is finite. Then, of course, what we have is what I showed you before. In other words, that this is an unbiased estimator because the expectations match, which is given through the first formula. But as well as this, you can also express the variance of this estimator through the notion of V, and also through the squared expectation just given as this. And so this is the main theorem behind Rhee and Glynn, and this has been very much used in the ideas of filtering for the past few years or so. So it makes a lot of natural sense, at least, to apply this to this idea of what we're trying to do, which is unbiased inference. And I just want to mention a very important thing about this, at least to my mind, is that Matti, who is a co-author of this work, has written a very nice paper in operations research, which has really shown a very nice connection between this Rhee and Glynn idea of unbiased estimation with the ideas of Giles and Hendrick on multi-level Monte Carlo scheme. So you can actually make a systematic relationship between these two ideas, which Matti has done. And I just find it a very natural but insightful work, which I recommend people to read if they're interested in this work. So this is the debiased scheme that we're actually going to use, and the estimator that we're going to use is this Z of one psi. So that's the key point that you need to remember from this. And then what we actually do from that is apply this to the scheme which we're using, which is the delta particle filter.
Yeah, sorry, just another quick.
Sure.
Yeah, actually can go back to the previous slides and just actually have a question about this distribution PL. So it seems like it's quite, kind of flexible, like you can choose any PL you want, is that right? I mean, certainly satisfy this condition here.
Yeah, yes. So that is correct. When I write this equation, there should have been a star here, which means that under certain conditions you can actually express this inequality. So yes, under certain conditions you can express P of L to be many things. Yes. I don't know if it can take anything, but most distributions or mass functions, yes, it can take.
Yeah, is it like any, I don't know, like any kind of principle, any criteria to pick this PL? It's like, oh, typically what kind of, what distributions you use in practice?
In practice, I think something such as you can use normal, uniform are very commonly used. There's a lot of recent insight into what choice of P of L one can use for particular inference problems or application models. But generally speaking, as long as you introduce some form of randomization, the scheme will work quite well, which is the nice novelty of this.
So does it affect the performance, different kinds of distributions, different type of distribution? Does you think it will affect the performance of the estimator, or?
I think if you look, I think if you consider a lot or many distributions, it may have some effect, but generally speaking, the difference is not so significant.
Yeah, thank you.
Okay, thanks for the question. Yes, so like I was saying, after introducing the debiased scheme, we now want to implement this within the delta particle filter, which is the sequential Monte Carlo method we will use within our particle MCMC method. So this is the estimator that we're going to use and actually to ensure the debiasing of the partially observed diffusion processes. And if we do this by taking the expectation of this quantity, then what we actually get is this coupled system. We get this system that we have right here, based on the coupling that I described to you. And yeah, we also have to assume that the variance of this is finite as well, and the same assumption regarding L to be distributed according to this PMF. So this is just essentially saying that using the notation that we have, that we can introduce the debiasing scheme that we have on the previous two slides. I believe that's it. Yeah. Okay, so the first two bits of the actual approach I've discussed, which is the multi-level Monte Carlo and also the debiasing scheme. But the last crucial bit that we really want is actually this important sampling type correction that we have. And before discussing what that is, I just want to recap to all of you that what we're interested in is the unbiased joint inference over this posterior distribution right here, where the inference is over theta and the inference is over the signal process as well. But there's one issue that we have if we immediately go towards the actual joint inference, which is that if we actually look at this delta particle filter scheme that we have a set of weights at some coupling. In other words, we have a coupling of weights where they are at one level and they are at a different level. So level L and level L minus 1. And it's well known that within particle filtering schemes that the weights should not be negative. But of course, with this coupling scheme, indeed, the weights can be negative, and this is something that we want to avoid and we don't want within our methodology. So what we've used is this IS type correction scheme, which again is by Matti, Jordan Franks, and another co-author of 2018, where they implement some particular correction type term, which is to actually compensate or overcome the idea of negative weights. I forget exactly what the exact type correction scheme is. It's quite simplistic to implement it in practice, but there's a lot of theory behind it and a lot of motivation. So all I know is that it removes the idea completely of attaining negative weights, which is something that one does not want within particle filtering schemes. And I don't really have much analysis on this, but again, if anyone's interested, I would recommend them to this paper to find out how to avoid this actual particular problem. So now that we have the three main ingredients in order to do the unbiased inference, like I said, you can actually split this into two particular phases. So the first phase that we have is that we're actually going to have a particle marginal Markov chain, Metropolis-Hastings method, where capital theta k is essentially the collection of thetas that we have, and x are the particles that we have. So we're interested in the joint inference over these two quantities right here. And we also have likelihood type estimates B star n of k. And then using the idea of de-biased multi-level Monte Carlo and the IS type correction scheme that we have, we essentially can come up with a new estimator, which we could denote as E, I is E, superscript I is subscript M, F, which can converge essentially to the posterior distribution that we're interested in, pi of infinity f. We have denoted this quantity to be infinity because we're essentially looking at the original continuous time setting before discretizing. And then what we actually show from this is that if we have this estimator on the left-hand side, then through the ideas of statistical consistency, we can indeed show that this is consistent as m goes to infinity with respect to the original joint posterior that we're inferring about. Okay, there are a number of assumptions that we need in order for this theorem and statement to hold. We need f to be an L2 function, and we need a number of other assumptions, which I forget at the moment, but yes, f needs to be an L2, and with a few more assumptions, one can show that this result actually holds, this consistency result. And so we'll get to the main theorem, this of the actual paper itself, which is a variance bound for the delta particle filter. And so in order to initiate and describe this theory, we usually have to assume a number of conditions, which I haven't stated, but they are usual conditions one would assume with the Feynman-Kac model for the diffusion process that we have, such as Lipschitz conditions and also linear growth, which I believe are two conditions. There are other conditions as well, but if we assume Lipschitz continuity, if we assume linear growth, and we assume some conditions on the hidden Markov model, then what we can say is that for a particular function phi, which is bounded in Lipschitz, we have a constant c which does not depend on n, l, or theta, such that the variance of this delta particle filter estimator is essentially given by this quantity right here. This is upper bounded. And then if we consider either Euler or the Milstein scheme, where Euler corresponds to beta equals 1, or the Milstein scheme, which corresponds to beta equals 2, essentially what we have is an upper bound on the MSC, which is given as this right here. So the left-hand side is the MSC, which I showed you in a number of slides before. And this bound that we have right here is very typical. This is a typical bound that one would assume to get if anyone is familiar with multi-level Monte Carlo schemes. So this typical bound contains information both about the variance and information about the discretization bias that you have. So for this quantity right here, this is the variance of our scheme that we're using, which comes in through this, which is the variance through the multi-level scheme. And this is just the discretization bias that we have from the usual Euler-Maruyama discretization of the stochastic differential equation. And so what this theorem essentially states is that in order to, what this theorem essentially states is that one can get a reduction in cost in attaining an MSC of order epsilon squared from epsilon to the -3 to epsilon to the -squared log epsilon squared. So this theorem is essentially a multi-level Monte Carlo theorem, which implies a reduction in cost for attaining an MSC. So this is important because it indicates that the multi-level scheme actually reduces the cost of this methodology. And the other theorem, which I haven't put in a theorem box, is essentially that this estimator is consistent with the overall joint posterior distribution that we're interested in doing inference for. Okay, so this is the main theorem that we have. And I've just given one slide before I show you the numerics, which is really to indicate how one can choose P of L and N of L in terms of maximizing the computational complexity and cost. So the costs for these multi-level Monte Carlo schemes is usually given in this summation right here. And the idea behind showing you this slide is that one aims to try and balance the cost of multi-level Monte Carlo through computing both P of L and also N of L right here. Okay, so the mean cost that we have associated with these actual schemes is given through this upper bound right here. And with these different schemes, depending on what we use. So for example, if we use the Milstein scheme, which we know is beta equals 2, where beta is just the strong order of convergence. If beta equals 2, which corresponds to the Milstein scheme, then if we want to get an optimal computational complexity for the multi-level Monte Carlo scheme, what we do is usually choose NL to be proportional to 1 and P of L to be proportional to this. So this is for the Milstein scheme. And then for the Euler scheme, what we're going to do is that because we know it's beta equals 1, this indicates that the scaling has to be a little bit different between these quantities. So instead, what we do is that we scale n of L to be 2 of row L and P of L to be 2 to the minus 1 plus row L. To the audience members, this may not seem so obvious or intuitive where this actually comes from. This is just to indicate that when one is introducing a multi-level Monte Carlo scheme, there has to be some scaling in terms of the number of particles and the particles that you use. And therefore, this is what these quantities are representing. And essentially, if one can do this, then you can get the associated cost, which I told you before, which is the reduction in cost from order epsilon to the -3 to this quantity right here for the cost. So this is not important in order to show the unbiased scheme, but it is important to indicate how one can computationally reduce the cost effectively for the multi-level scheme. And so with this, I'm just going to essentially show you 2 examples of this. Well, 3 examples actually. The first slide is going to indicate the performance of these methods on 2 one-dimensional experiments. The first is an Ornstein-Uhlenbeck process, which we consider on the left-hand side. And the second is just a one-dimensional geometric Brownian motion, which is on the very right-hand side. So for the Ornstein-Uhlenbeck process, it's just a simple stochastic differential equation, which many of you know. But for the one-dimensional geometric Brownian motion, we're going to consider this original process right here, which uses the same notation as before. X of t is just the signal process, wt is the Brownian motion, and y of p essentially is just the observations that we have, which are taken at discrete time points. But what we can do to make it to make the stochastic differential equation look different is that if we actually label x of t or x to be log of u, and by taking Ito's formula, we can actually redefine the stochastic differential equation to the very bottom. So this is the stochastic differential equation for geometric Brownian motion. And the hyperparameters or parameters of interest we're interested in are a, which are going to take the form of the exponential of theta, where theta are essentially where theta again is just the parameter of interest that I told you at the beginning. And what we're going to do essentially is run 100 independent chains in this particle Markov chain Monte Carlo method and see how the MSC performs as we actually go further in time. So these plots correspond to MSC versus cost plots. And this is for the Ornstein-Uhlenbeck process at the very left. And this is for the geometric Brownian motion. So there's a number of different colors that you see. So what we're actually going to do is show you 3 lines on each subplot. The red line is going to correspond to the MSC given through this equation, and the magenta curve is going to correspond to the actual delta particle filter that we use within the particle MCMC method. And the blue line is going to, the blue line is going to correspond to our methodology, which is the delta particle filter in the PMCMC method. And the magenta is just essentially going to use the ideas from the exact methodology in the particle Markov chain Monte Carlo method. And the rate that we're actually going to compare it with is the canonical rate, which is just the cost to the -1 or 1 over the cost. And essentially what we want is to show essentially that the decline in the MSC relates to this actual decay that we have. And as you can see that throughout these methodologies that they are very similar, we start to see that the actual exact methodology, the performance is slightly better with the magenta curve. And this is because for one-dimensional diffusion processes, they work exceptionally well. But interestingly, if we see the blue curve, which is our methodology, it starts to increase a little bit. Now, this is not related to our methodology per se, but we have repeated experiments where it is more constant rather than plateauing as it would if we actually increased the number of iterations. So this is for the one-dimensional Ornstein-Uhlenbeck process. And for this, what we have instead is just the geometric Brownian motion with a slightly different rate that we're interested in, which is the subcanonical rate of the log cost to the -1. And as you can see, all of these procedures that I'm comparing, which is the MSC, the exact methodology, and the methodology that I presented in this presentation, all seem rather consistent with the geometric Brownian motion case. Okay, and the reason that this is canonical compared to this is because the canonical rate actually corresponds to the case of beta equals 2. And the reason that we can actually use the Milstein scheme for this is because we have a constant diffusion coefficient, a constant drift term. So this is geometric Brownian motion, but if you consider Ornstein-Uhlenbeck, you would have a constant diffusion process, constant drift term. Therefore, this corresponds to the Milstein scheme. We can use the Milstein scheme. Therefore, we get this canonical cost that we compare. So these are the 2 plots for the one-dimensional examples. And what we do essentially is the exact same for a two-dimensional Langevin equation, where we're interested in targeting this particular distribution, whereas you can see we have a number of parameters of interest, A1, A2, and also A3. So there's 3 parameters of interest, which are randomly distributed and randomly chosen as well. The observational process that we have is again discrete, and the signal process that we have, of course, is a continuous time stochastic differential equation. Now, to compare our methodology with the exact methodology was difficult, because if you remember what I said, in order for the exact methodology to work, you apply a Lamperti transformation where the diffusion coefficient then becomes constant, and then the drift term is actually in the form of a gradient of a potential function. But this gradient of a potential function is quite complicated. Therefore, the actual implementation of that methodology for this process is very difficult. Therefore, the only thing that we could really compare our methodology to was the actual rate in the MSC. And as you can see right here, MSC is just the MSC corresponding to this equation right here, and MSA2 is just the methodology that we've used that I've described. And again, it's fairly consistent with the actual canonical rate that we see right here. So it gives an indication that our methodology is actually working. And for the one-dimensional problems, it seems to perform reasonably well, at least compared to the exact methodology, which beforehand we knew would be more subpar, as those methodologies work very nicely for one-dimensional diffusions. So these are just results in both 1D and also 2D as well. So to summarize, the motivation goes to the heart of trying to do unbiased inference for a wide class of diffusion processes. And the diffusion processes that were interest to us were partially observed diffusion processes. Unbiased inference has been a very hot topic, but it's also been a very challenging and difficult topic. And there's been a lot of ongoing work trying to overcome these issues, both in terms of how you can apply it to different diffusion processes and also to reduce the computational complexity associated with this. So what we aim to show from this was that one could do unbiased inference for the diffusion processes of our interest. And we were able to do this using ideas and techniques from multi-level Monte Carlo, debiased Monte Carlo, and an IS type correction scheme that I indicated to you a few slides ago. And we verified this through the consistency result, as well as demonstrating that we can reduce the complexity associated with attaining an MSC of a particular order, and demonstrating this through a number of examples. But based on this, I think there's a lot of interest in further developments that can be made from this, both in the directions that we considered, but alternative directions as well. One of the things that we would like to do is to consider a fully parallelizable implementation, especially with the IS correction phase. Based on that paper that I showed you a few slides ago by Matti, he indicated that it is fully parallelizable, but we would like to at least test this for a lot of diffusion models, which can be quite computationally difficult. And that's something that we're very much interested in for future work. Another interesting work is to actually consider more multidimensional diffusion processes. We've only considered for this work dimensions 1 and 2, but of course there's many diffusion processes which make more sense to model multidimensional and which are naturally multidimensional as well. Of course, this will be more computationally costly. This will be more costly in practice, and therefore using the ideas from the first point may actually be more beneficial for the second point. And the last point that I want to make, which I think is also very relevant to the ideas behind this work, is to consider some sort of connection to Blanchett's work on exact methods. So even though there is no existing theory for Robert's initial work for multidimensional diffusions, Blanchett's work actually ensures that one can actually do exact sampling or exact simulation from diffusion processes in a very complicated and theoretical way. The only issue with his methodology and his co-authors is that there is an infinite mean cost associated with doing that. And this is the exact reason why we actually never considered using his methodology for these examples right here, because it would just be so cost effective. It would be so costly that it would take a lot longer to actually run these simulations. But that being said, there is a very interesting insight in how he can actually show that one can get exact simulations from these diffusion processes. So I think if some connection is made between his work and the work that we've done in this paper, it could potentially offer some more capabilities in handling more multidimensional diffusions, maybe in a very nice way as well. But this is still ongoing work. There's still a lot of challenges to develop this work, but it is a very promising field and a very interesting one as well. So this concludes my talk for today. Thank you again for your attention. And if anyone is interested in reading more upon this, I would lead them towards this paper that has been recently published. And yeah, thank you again for your time.
Thanks a lot. Very nice talk. So any questions from our audience? If you have any questions, please unmute yourself, ask directly. Go ahead.
Neil, very nice talk. Can I just ask a couple quick questions? If you go
course.
back to your slides where you had your numerical experiments, the one before, can you explain, I'm sure you have explained, but I was lost a little bit. Can you explain what's this MSE, MSE2, and MSE3 and the cost to the power of minus one? What are they representing for here?
Okay, so if you remember what I said with multi-level Monte Carlo methods, you want to reduce the cost associated with attaining an MSE. So the usual way that you verify multi-level Monte Carlo schemes is actually to do these plots where you look at the cost versus the MSE and you look at the rate, which in the canonical regime that we have is cost to the minus one. So these plots are just to indicate that the multi-level scheme that we've implemented actually works. And so our methodology that we've implemented is this magenta scheme, which is, the methodology that we've introduced is actually this blue scheme, which is the very top one. The red line is just computing the MSE of all of these different replications. So these are just replications based on the chains that we have through our particle MCMC method. And the red line is just the MSE or the average of all of these replications. And the blue curve is our methodology, and the magenta curve, which is the bottom one, is the methodology that I described at the beginning, which is the exact methodology. And so what we're doing in this is just essentially comparing our methodology to theirs for these different plots.
Okay, so the vertical axis is the MSE, and
yes, that's correct. So this is the MSE, and this is the cost that we have.
So it looks like the method you're proposing in blue is kind of slightly worse than the exact, but still quite close enough. Okay.
It's slightly worse. We've repeated experiments where it's a lot more constant rather than straightening out. But yes, it is very close. But in all the experiments we did, it was a little bit worse than the exact methodology.
Okay. Just one final quick question. Can you compare the cost between the method you propose and, for example, the exact one?
So the cost that, so for the cost for, so when I mean cost here, I mean sort of the iterations that we have, but the computational time to run the experiments was quicker for our methodology, at least anyway, just by a little bit. And I think the reason for this was because of all of the different implementations of the debiasing and the multi-level that we implemented. So there wasn't a significant difference. It was a little bit cheaper, but there was no real difference between the computational time.
Yeah. Any other questions from audience? If not, actually, I have another question already. I know I already asked a number of, but I have a very, very quick one finally. So I understand correctly. So the kind of the problem we are doing is kind of still in the framework of a sequential Bayesian filtering problem, right?
Correct.
Okay. So can your method be extended to the kind of the smoothing case?
Yes, I believe it can be modified to the smoothing case, quite easily. We've had discussions on this, and we were actually interested in implementing that for this paper. I forget the reasons why we didn't include it. It's not because it didn't work. We do believe it will work. We wanted to try it out, but yes, to answer again, I do think it can be extended, and I don't think it would be very difficult to extend it as well.
Yeah, but in that case, my understanding is that you probably can't use the particle filter anymore, right? You have to do something else.
Yes, you would have to do something else. So you could use some smoother algorithm that you would have to use, but the methodology, of course, would change. The theory would slightly change, but at least in terms of the implementation of combining the multi-level and the debiasing scheme, I think those ideas can be implemented to many smoothen algorithms just like they can for this filtering scheme. I don't know if the theory would directly apply or would hold, but I think methodologically, I haven't tried it, but yeah, with a little bit more difficulty, I think it should be able to work.
Okay. Yeah, that's good to know. Thanks. Any other questions? Yeah, if not, let's thank our speaker again. And yeah, if you and Neil, could you please stay for a little bit longer, just in case you know, kind of some audience may have extra questions.
Sure.
Yeah, thank you.